from the Professor Cook's lab, and maybe I'm the last Korean speaker. And first of all, would like to appreciate the organizer and professor for the great opportunity. And before the presentation, I would like to say something to Japanese. 東京大学の皆さん、おはようございます。ここでお会いできて本当に嬉しいですけど、今から要員園になったらと思います。もし発表が通りなくてもご理解お願いします。とにかくよろしくお願いします。Recently, a growing number of researchers have been applying the AI in our field. I think AI is an alternate method to overcome the inherent limitation of the existing numerical model and improve the prediction model accuracy. So several studies already have been focused on defining the predictive skill to answer. This implies that AI methods have the potential to enrich our understanding of answer. However, attempts to use the AI techniques for deeper exploration of the physical fundamental of answer association remain insufficient compared to forecast. So I want to make a simple deep learning model for more understanding of answer like GCM. So, one study was published in a couple years ago. In this study, a simple statistical model was developed to predict answer using several climate components related to answer, the other Bayesian component. And they suggest that it is possible to understand climate dynamics without the complicated process if we have a good understanding of them. So considering insight from two things, we study simple method using AI, which means the low-dimensional deep learning model for answer simulation. So for comprehensive understanding answer, we briefly explore the application of deep learning to simulate its characteristics. I refer to this answer simulator. This is flowchart of my research. First one is I will introduce my deep learning model in detail, and second and third part is I identify the answer characteristic using this model in two directions. To ensure sufficient model training with stable data, we use the 1,000 years of GFDM model data, which is the climate model and is known to simulate well answer dynamics in many previous studies. And also, as you can see, I choose the Pacific Ocean variable, which are related to the answer dynamics. And we also use the SSTs in the Indian Ocean and Tropical Atlantic Ocean SSTs to identify the relationship with answer. So we then perform UF analysis on each variable, which allowed us to extract the main variability while reducing lower dimension, which we only use the three leading UF mode. The first mode, Pacific Ocean SST first mode, very related to Niño 3.4 index. So I will introduce my model architecture. So total number of input variables is 15 variables. For the deep learning method, we use the most basic method is the DNN. So this part is the deep learning part of about the technical methodology. So from input layer and along the hidden layers, the same 15 variables are generated for the output variables. Because the input variable and output variables are identical, so we can generate output auto-regressively, have one seasonal refer the previous study slide. This is structure of my ENSO simulator. For example, if we input some particular seasonal data into the first seasonal model, then generate the next season model output and repeat this continuously. After that, we can get this recursive structure. However, if I do long-term integration using this process, then we cannot obtain the expected result. Then why? I think in time series, you can see in the time series figure, the red line is indicate the generate deep learning model's output time series. You can see initially it oscillates and variability almost disappeared over time. This phenomenon is called to damped oscillation. This is because that many previous studies said the observed ENSO has stable mode characteristic with the external forcing rather than unstable mode. So its amplitude slowly decrease over time. So this problem may occur in the almost recursive AI model. So then how can we resolve this problem? In our study, we consider the stochastic noise. This is stochastic noise. We added reflect the ENSO variability excited by stochastic noise forcing like real ENSO, and using the prediction error, and we extract some covariance pattern from the EOF. And after that, we add this noise term in each prediction step. After that, as a result, the amplitude is maintained over time compared to without noise experiment. Now I can conduct the long-term integration. So I will show some result. So to analyze the ENSO, we integrate over 1,000 years, and this result has its initial 300 result time POS TPC1 time series. Upper side is JPDL and bottom side is DNN. You can see in the bottom side the irregular interannual oscillation and just some strong and weak period decadal variability period signal like GFDL. So overall, I skipped many things, but overall, the deep learning model is pretty good at simulating the statistical characteristic of GFDL ENSO. So from this, I firstly checked the ENSO spatial pattern compared to GCM. Both results are similar spatial pattern, and the number of occurrences is very similar. Yeah. So and after that, I also can capture the ENSO diversity like CP and EP. I skip this. I can capture the ENSO asymmetry from the residual pattern, which means the El Niño plus La Niña. So this deep learning model can modulate the ENSO asymmetry, and also I identify the ENSO diversity in EP and CP El Nino, the results are comparable. So it also simulates where ENSO that occur during strong and weak period of decadal modulation. And furthermore, I used the other Bayesian variable we could know the relationship between ENSO and other portions. To verify each Bayesian impact, we conduct decoupling experiment. Simply, if we want to remove the Indian Ocean impact, we just set the zero. We set the zero value to the zero continuously for Indian Ocean variables. So this is the power spectrum of each experiment. You can see looking the orange line, we can see increase of the amplitude and periodicity of in Indian Ocean decoupling experiment. Despite the simple handling and cheap cost experiments, it is consistent with in previous GCM studies. Actually, the Indian Ocean to contribute to the rapid transition of ENSO phase. To better understanding, I plot the ENSO evolution from peak to decaying phase. In the Indian Ocean decoupling experiment, you can see the slow transition than control experiment. So this result has already been shown in previous studies. So third part is the ENSO prediction. Due to using the noise, we can easily make the noise ensemble, and deep learning model has a quite good prediction skill. And also it has some SPV when we predict from MAM to JJA. I also check about the role of the other Bayesian in terms of ENSO predictability. This result suggests that the inclusion of variable from other Bayesian is important for ENSO prediction. Beyond the predictability, it is also important to understand how much each input variable contribute to the output prediction skill. So I conduct the kind of explainable AI method called contribution map. The contribution map is designed to know which input variable has a larger contribution to output variable by modulating the input variable. Easy way to know which input variable are important for the specific predicting output variable. You can see the larger RMSD, which means the darker color, indicate that the particular input variable is playing a relatively significant higher role in predicting ENSO. So the Pacific Ocean PC1 itself and Pacific Ocean Wind PC1 are higher contributor for ENSO prediction. Also, we can identify the comparison scatter plot with control experiment. For example, in this figure, considering EOP spatial pattern, the westerly wind occurred in Western Pacific region, then in MAM season, it is significantly important to predict the DJF Reno index. Also has a non-linear relationship because whereas strong westerly wind in Western Pacific can tend to be more efficient in triggering in El Nino, but on the other hand, the La Nina is less efficient. So I analyzed all variable on the ENSO predictability, and this is summary of my presentation. I developed the ENSO simulator using deep learning, which can simulate GCM characteristic in the long-term simulation, and also I can get some ENSO predictability source from this part. I think it's a great tool for easily trying various experiments with lower computational cost. So, thank you.